Let's learn the table lookup principle next. Relatively speaking, there are many basic concepts of routing. So we must first lay a good foundation. I've drawn a reference picture for you now. I now make a connection to the line. Certainly. I drew this picture for the convenience of the lecture. If you are planning a project in the future, such planning is a failure. But the lecture, this is a very typical case. For example, it is 192.168.1.0, 24-bit mask. This is a network segment behind this device. This is a 25-bit mask. This is a 30-bit mask. I teach you how to draw. Draw a line here. Add an arrow here. This means that there is a network segment behind the device. Okay. This is 3 network segments. You will find their 192.168.1.0 place is coincident. Let's say this is device 1. This is device 2. Device 3. And device 4 below. We plan the next hop for them. Suppose here is 1.1.1.1. 30-bit mask. Its peer is 1.1.1.2. Suppose here is 2.1.1.1. Its peer is 2.1.1.2. Further down this is 3. 1.1.1. Its peer is 3.1.1.2. They are all interconnected. This is the interconnection address between them. Now no matter how. In short, now I have learned the following routes. Whether static or dynamic. Now this one by one route. Learned all the equipment. Then these 3 routes will be added to the table. There is a routing table on the device. 192.168.1.0. 24-bit mask. Add all 3. Because the identification must be a different destination network segment. So it must be added, regardless of how the rear equipment is connected. But what is happening now is that all tables are added. So now comes a data. This data will go to 192.168.1.2 in the future. So where is the next jump? Think about it. Now comes a data. The destination address of device 1 has been reached. 192.168.1.2. There are now 3 options for the device. Here, here, and here. So where will it be sent from? When the device receives such a route, how to judge which line it should go to? Now there are so many. Which one should be matched? First the local will calculate. When we talked about ARP before, we said that take your own mask and add the IP of the peer. Match with yourself. Router 2. Now the data is going to 192.168.1.2. It will take out all the local matches and calculate them. Look. 24 can match it. The calculation is the 1.0 network segment. Both 25 and 30 are calculated with it. Whoever counts. Calculated and found that this network segment. It means that the data is now going to this destination. All can match. Then the longest mask will now be chosen. That is, we'll select a mask of 30 bits. Since the mask is the longest, represents a longer network bit. Host less. Then the purpose of visiting in the future. Although it is a destination network segment, but in the end it is still a precise destination IP address. The fewer IP addresses covered in a network segment, it means that the network segment is more accurate. For a 24-bit mask, there are 254 usable addresses inside. That is, if it matches the network segment behind the device, it has 254 addresses to match it. But if now go to this 30-bit mask, it only has 2 precise addresses in it. So, If all three can match now, we will choose the one that believes the mask is the longest, because it will be more precise. If this 24-bit mask is matched, it may end up going through a few more routers to arrive. So the path we choose is one step. Choose the most accurate. This is a lookup principle. Then there is a difference between the table lookup principle and the table addition principle. The lookup table principle is called the longest mask match. That is, if there are multiple matching routes locally, it will be forwarded according to the longest mask. Suppose. Now comes a new data. Go to 192.168.1.4. Then it should go to device 3. That is, go to the 25-bit mask here. Then if 1 comes now, 192.168.1.130. The next hop should go to device 2. Because now the maximum of 25 bits can only reach 127. Here are some differences between them. So for now in the routing table, there is a more magical route, called 0.0.0.0. The mask is also 0.0.0.0. Route like this. Let's call it the default route, also known as default route. Let me explain the default route. Draw a simple picture. This is an export router of your company. This is the operator. I won't draw the switch. This is a PC from your company. The router will then access any internet data. Find its gateway, because it must cross the network segment. Find gateways across network segments. The data arrives at the gateway here. Its destination IP now relies on a DNS. The destination IP must be resolved locally. Then it will be sent to the router. For example, data is now going to 2.3.4.5. Such an address. Let's say this is Google's address. Now this device. If you want to help forward, this device must have an address to 2.3.4.5. Assume that a large amount of data will be accessed every day in the future. All such addresses. This terminal has to send data to the public network every day to access services that vary from company to company. Then please, is it necessary for every route of this export device? There are about 800,000 routes on the entire public network. Do you want to go to every address on the public network? Do we need more than 800,000 routes? This device cannot bear such a large routing appearance. If the future comes a data, look up data from the routing table. Match the previous route. Then forward it. That theoretically, I go to the public network. As long as I do the business of the operator, we all take the carrier's equipment. Can go anywhere. Export this device. If there are more than 800,000 routes now, send a piece of data. When searching the routing table internally, more than 800,000 routes retrieved one corresponding forwarded out. From sending data to Google to receiving its reply, maybe 7 or 8 hours have passed. The data has not been sent yet. Secondly, the routing table itself cannot bear such a large appearance. Who will configure it including this appearance? Does the engineer need to manually enter one by one? It's out of the question. If you want to run a dynamic routing protocol with the operator's equipment, first will not run. Second, even if it actually runs, do you need to rely on dynamic routing protocols to pass 800,000 routes to each other? This is too exaggerated. So we have a simple way. Since I now want to access any business on the public internet, all walk operators, then I will write a route now. This route represents all routes. That is, represents all addresses on the public network. Even all addresses in the world that conform to the IPv4 address configuration format. Write all. No matter where the data goes in the future. Take this device for the next hop. For example, this is an interface for interconnection between operators and devices. You will also assign addresses in the future. As long as you run services with fixed bandwidth, there will be a fixed address to connect with you. There is a static. We'll point to the operator on this device. As for how it got back, don't worry. Now for business. There is a route for the egress device, called the default route. Represent any piece of data in the future. Can match these 40. 4 zeros represent unknown. Represents the least precise, because its mask is 0. The longest mask match means it is more accurate. The longer the mask, the more accurate. Its mask is 0. Then it must be the least accurate. Some students may think that 800,000 routes are not too many for routers. Although it is a network device, the hardware used must be more advanced than PC. But we collectively call it a piece of hardware. Its computing power is also limited. If between devices, even if the data is sent out, query locally. How can more than 800,000 routes reach this device? Words learned through dynamic routing. Does running a protocol interact with each other so much? Then the overall bandwidth does not need to do other things. Just interact with the routing table. Business data cannot be forwarded at all. Suppose now there is a route 123.1.2.3. For example, next hop right is null. If there is a data coming now, can it be matched? Originally, if there is no this route to come here, just drop the packet. A data came. Device 1 helps it forward. Check the routing table and found no. This data is discarded, because the device can't help it forward. Now a route comes in on this device. Is the default route. Now if we match. Can it match? OK. Is allowed. For corporate exports here. Write a default point to the operator. Go to any business on the public network in the future. As long as the data reaches the gateway, it receives this data to help forward. They all go to the default operator. Same. Send this 123.1.2.3. It is possible to match. Only here because I didn't draw another line. Write next hop. I can only write a none to it. This thing you will learn in the future NP stage. I now ask you another question. Now comes a route 192.168.1.3. If send now, who will this traffic be sent to? OK. Will be sent to device 3. Because the following does not cover this address. So will 1.3 match this default route? Look at the data now. It also matches 4 zeros. It does not limit each bit. It seems different from others. Will not match the default route. The concept of default routing is, if there is now a route, at this point its destination and mask are both 0. In this situation, it represents a default route, also known as default route. So if it's a route like this, it can match all IP addresses in the whole network. But why doesn't it match what we just said? For the default route, since its mask is 0, it is a route with the worst matching order. Only when there is no local route to match will match the default route. Now comes a data. Check locally first. When it is determined that there is no precise route in the routing table, we'll match it to the default route. But unfortunately, there is a route here. Can help with precise forwarding. Then this default route will not be considered. Only as we just said, such a network segment sent over will consider the default route, because there is no detailed route locally to reach it. So the default route will be considered. Here are some relations between them. The above is about the addition and lookup of routing tables. We make a summary. For routing, if you choose to add routing table now, multiple routes now want to appear in the routing table. Then to make a comparison, to confirm the final route can appear in the routing table. This is called the principle of addition, followed by table lookup. If the current data arrived at a router, the function of the router is to help forward data. There are now multiple lines can go to the destination network. Then at this time, the local will be based on the routing table that has been generated. Select the one with the longest mask and send it. If now can't match any exact route, then if there is a default route locally, just match the default route and send it out. For example, now there is a default next hop. Point to this device. Just give it the traffic. There is a route to 1.1.1.1. Put the traffic to the middle, instead of going down. Here are some of the principles we talked about. Finally, let's look at the lookup table. Longest mask match. For example, I can now write 4 static routes. There are 4 S. Stands for static. Can point them to the same next pick. In theory, as long as the principle of addition table is met, it can be added. It doesn't matter if the next hop is the same, as long as the mask is inconsistent. Different purpose network. Different network segment. So now no matter the next hop is inconsistent. Add all. The routing table we are talking about now. It is referenced to the destination network. As long as the following mask is inconsistent. Different destination network. Go to the only destination network. There will be a unique route. It will be processed by adding table principle. In addition, what is the difference between the default route and whether it is null? This may be misleading everyone. Logically speaking, we can add another line here. Add a device here. Let's say it's 4.1.1.2. 30-bit mask. It is also in the same network segment as it. This will write the next hop to here. Just because I didn't draw this device, I can't write a next hop. So I can only write a simplest way. The next hop can be represented by null. It's like I dropped it into a black hole. Black hole routing. But the NA stage will not learn this. The default route also points to the next hop. If the future comes a data arrives here. These 3 routes do not match. Data go here. Match the words. It is equivalent to such a route. Next hop is here. Then the null I just wrote is also the next hop. Only, the representative is not to send out this route. Instead, the route is discarded here. Let's review next. Whole router forwards packets. When the data is forwarded as a whole, each router, actually, the parameters in the second layer are to be modified. Then why do you want to modify? When we learn the routing table of the complete body, everyone should understand. Because every time RA performs routing table lookup, local will see what is the outgoing interface on the device now. Now after this route is forwarded, this data is sent to the next device. For example, now the data arrives at the device. Then before arriving, when sent from the previous device, the next hop address is the address of the left interface of the router. The device forwards this data, sent to RB. So now the destination IP address. It is the address of the left interface of RB. When we do data encapsulation, if the third layer is the address of this interface, and both of them are a directly connected network segment, from RA to RB, When it is making an ARP request. To request the MAC address of RB. That is, when this data is sent. The destination MAC is the MAC of this interface. The next time you retweet, destination MAC is its MAC. Further down the target MAC is its MAC. This is the purpose MAC. Let's look at the source MAC. When future data is forwarded as a whole, the source MAC will be the MAC of the outgoing interface. For the current data, each forwarding through a layer 3 router, separated by the interface of the router. On each different link, both the source MAC and the destination MAC will be changed. The router must know the next hop outgoing interface to send the data. Therefore, when the router forwards data, it will have some corresponding problems. The source MAC and destination MAC will be repackaged. This parameter will be changed. We will use the MAC of the outgoing interface as the source MAC. And the address of the next hop is used as the destination MAC. This is a concept between them. That is, data arrives at the router. Disassemble the second layer. Then look at the destination IP of the third layer. And then proceed to retweet. Forwarding process. The source port and destination port of layer 4 are unchanged. The source IP and destination IP of the third layer are unchanged. The source MAC and destination MAC of the second layer are always changing. Okay. Next, we will start to officially enter the part of static routing. What we just said are some basic concepts of routing. Static routing refers to manual configuration and maintenance by administrators. For example, now there is a routing device in the company. All routing entries inside. In addition to direct connection, I typed them one by one. For an enterprise network. In fact, only static routing is enough for small enterprise network. Also used by large enterprise networks. But it is not used as the main, because it will be more troublesome. As for the reason, we are in the process of experimenting. Can come to discuss. Let's first look at. This is the current terminal. Usually, the gateway is generally configured on a layer 3 switch. If I now send traffic to the gateway to export equipment, then export the equipment to the operator. This is a process of flow. We are often in the early stages of learning. The easiest thing to overlook. Traffic now goes to the gateway. No problem. Direct connection between gateway and egress device. No problem. In the future, we will write a static route pointing to the operator. No problem. The data can be exported as a whole. But what we tend to overlook the most is the how did this data come back? The operator now needs to reply data packet to these devices on the internet. For example, now the left is a network segment of 1.0. On the right is a 2.0 network segment. Then when the final data comes back, corresponding to return to 1.0 and 2.0. Otherwise the data will not come back. This is when using static routing. A more tedious part. You have to specify. This drawing is relatively simple. Let's discuss a slightly more complicated scenario. I draw it casually. Normal drawing is not like this. Real networking. It's not going to be grouped like this. Let's say this is some router. Simply make a connection. We are not discussing structural issues today. Assuming the current topology. That's how it's connected. For example, this device now has a network segment. More than one segment. There may be very many subnets. 1.0, 2.0, 3.0 etc. And I also want to subnet it. ABC that is not the main class is used. We also have a lot of subnetting. Then there could be hundreds of subnets. There are so many network segments on the left side of this router. The rightmost router is assumed to be 6. This is 1. For example, a PC is connected here to access the following network segments. If you want to access the network segment of 1.0, then we have to write the root in the middle. The characteristics of static routing are to write one by one. For example, if you want to go to the 1.0 network segment from here, then write a. Not only this device needs to write. The equipment that passes along the way should also be written. For example, the current route is like this. Then the 2 devices. There must also be hundreds of subnets behind. Then each has to be configured individually. Some students may ask, can it be glued after it is configured? Can't. Because the next hop is different on this device. For example, the next hop is the interface address. On this device say, the next hop is this interface. On this device is this interface. So there is also no possibility of bulk copying. Of course we can modify the next hop in the TXT document. Can but don't have to. Go to 1.0 like this. Go to 2.0 like this. Go to 3.0 like this. This is what we say. You need to configure manually. This is a characteristic of static routing. Then you have to write hundreds of articles. All the devices in the middle have to write these hundreds of entries. So compared to, it is more cumbersome. And now it's just traffic. Finally the data has to be returned. This device only knows how to go to 1.0 now. But it doesn't know how to get to the PC. So in the end this traffic have to keep pointing back. All the equipment along the way. Two-way routing must have. Otherwise, the traffic will not pass. Let's take ping as an example. Data goes back and forth. Then when the data comes back, there must be a route. So the limitation of static routing is that if there are more devices in the future, when there are many network segments, it's a little hard. It doesn't fit well. Because every node has to write. Over workload. And more error-prone. Not easy to troubleshoot. Because it is written statically. If you look at it, you have to look at it one by one. Dynamic routing protocols are different. If some problems arise in the middle. For example, add a network segment. Delete network segment. It can synchronize itself. As long as the dynamic routing protocol is running correctly. Then it won't have any problem. But the first routing configuration we learned. Definitely a static route. Let's start with how to configure static routes. This is a command. Everyone can remember. Show run. Include IP route. That is routing that is currently running on the device. It is the route I configured for it. There are 3 ways to write routing configuration. This is the router for RA. For example, from here to start a writing. Which network segment to go to in the future? Which address should the next hop go to? That's one way. We don't need to look at the picture above. Just look at this configuration. It means I have now written a static route called IP route. Then the destination network segment is 192.168.1.0. The mask of the destination network segment is 3,255 and 10. That is a 24-bit mask. But it's not allowed to make a bar 24 here. Spaces are also not allowed 24. Must be 3,255 and 10. Then specify an outgoing interface. That is, go to the 1.0 network segment now. Specify an outgoing interface is 10. The second configuration. Destination segment. The mask of the destination network segment. Plus the IP address of the next hop. Third way. Destination segment. The mask of the destination network segment. Plus the outgoing interface. Add the IP address of the next hop. Okay. What is the difference between them? First, the top one is not recommended. I would never recommend that you write like this. Because under the current Ethernet, it will have some problems. What is the specific problem? Let's talk about it in detail later. The second method is the one we use the most. When you go to configure in the future, use the second. No other. The third is the most comprehensive. Can but don't have to. Not necessary for most cases. If in the future you will learn scenarios that must be specified as such, you just go to study alone. It has very few application scenarios. Now most of the configuration will focus on the second. This is the most common way now. Let's first discuss. Why don't you suggest that you write an interface? Let's look at this picture. I told you before. If we look at the topology in the future, this one line connects 3 devices. Indicates that this is a switched network. It's like a switch is connected in the middle. This is a switched network. It means that they are all on the same network segment now. This is a relationship between them. Now 3 device interfaces. In the same network segment. So now we have a problem. If now RA. If you want to go to 192.168.1.1. If it is an outbound interface, then there will be corresponding problems now. Data can come out of this interface. This is no problem. But after the data came out, whether to go left or right, this we have to consider. Because there is no provision for the next hop. So what exactly is this data going to arrive at? Our RB interface. Or our RC interface. Don't know. So it creates problems. That is, if only the outgoing interface is specified. Under the current network, multiple devices can be connected through a switch. Let's say it's a switch in the middle. Then they can all be in one network segment. Now I want to forward a data to device 4. For example, data arrives at a network segment. Is behind it. That for us. Only the outgoing interface is specified. Traffic is sent from here. But I don't know where the next jump will go. So in general, we'll not specify the outgoing interface. Like in this picture. If you want to visit 1.1 now. Look. If I want to visit 1.1 now. Go left. If bad luck, only one outgoing interface is thrown out. If you go to the right, the traffic will be blocked. So it creates problems. Since it creates problems, then why is this outgoing interface? Will it appear in our PPT? This is also a problem. Let's look at the line in the middle. When we talked about the transmission medium before, I told everyone, this cable is called a serial cable. The link it identifies. Point-to-point link. It is an interface of one device connected to an interface of another device. There will never be any other equipment in the middle. Like we just said. A route. A switch. Connect multiple routers. Actually they are called logical interconnections. They both use switches. Can connect to each other. But for point-to-point links, it is not possible to use equipment, such as switches in the middle. Point-to-point link. As long as the outbound interface is specified, it means that the final traffic must reach the peer end. After the data is out, can't get anywhere else. Only to the peer device. So as long as there is a route to the peer, to send the data. Then under this link, serial line 2 interfaces. It is possible not to configure the same network segment. That is, on the left is 1.1.1.1. On the right is 2.2.2.2. As long as there is routing, direct communication between them. That for the current Ethernet. Both ends must be configured with the same network segment. If you do not match the same network segment, will create some problems. This involves a data encapsulation problem. I'll just tell you. The device on the right does not need to encapsulate the destination MAC. Because for a point-to-point link, the device on the left can directly find the device on the right through the address. So no need to get the MAC on the right. And what we're talking about? Networking based on switches. Such Ethernet. That is, LAN networking mode. The left device must find the MAC of the right device. Because there can be multiple devices in a LAN. Then need to be on a link. Locate which is this device. So you need to send an ARP request MAC. The point-to-point link does not need to send ARP. Here's the difference between them. Let's move on. Let's take a look at the configuration of static routing. We're about to get into the experimental part. The experiment I assigned to you is the one in the lower right corner. You can do all the experiments in class by yourself after class. We turn the device on. Start up. I use both devices. Want to do a little experiment? I'll take a screenshot of it now. Put it in the picture and say it. Now here are two devices. For the right end, I configure it with a loopback address. Can simulate a network segment behind. Plan the address. 192.168.1.1. On the right this is 192.168.1.2. I want to simulate now. A network segment is connected behind R2. It is the network segment of 1.1.1.0. There is a way. I can connect another router here. Configure 1.1.1.1 for this interface. Configure 1.1.1.2 for the peer. This means that R2 now has two interfaces. One interface is 1.1.1.1. One interface is 192.168.1.2. Then it is equivalent to available from R1 here. Access to the 1.1.1.0 network segment of the backend, which is equivalent to I want to simulate now. There is a network segment behind, whether it's a PC or a device. In short, a new network segment has been added here. I hope that the simulation can reach this network segment. It is equivalent to adding a new network segment. But it is relatively cumbersome. When going to configure, I want to pull an extra device. Power on the device. Name it. Configure it with an interface address. Then configure an address for its interface. Represents that there is now a network segment. This way is troublesome. So when we experiment, would not choose this method. The way we choose is open a loopback interface on this device. Configure an address for the loopback interface. That means there is a corresponding network segment behind this device. Then we don't need to pull another device. No need to configure an internet address for it. This means that the rear of the device is now equivalent to a router's virtual interface. Configure an IP for this virtual interface. Then this interface has an advantage. Just never down. This interface will not be down, because the interface will be damaged. But the virtual interface will not be damaged. There is such an interface on this device. Then often for routers, the address of this interface. We can also use telnet to this device. Debug it. But this interface, not for experiments. We will learn many configurations in the future. The relevant configuration inside will use the loopback interface. But at the CCNA stage, if we choose the loopback interface, just use it to simulate a network segment. We can do it in two ways. One is the loopback interface on the device. One is the interconnection interface. There will be some difference between the two. But usually, the loopback interface is not used much. This is the content of NP. That is, it's not just for experimentation. Right now such an experimental phenomenon was simulated. I first configure the address of the device base. It is slightly slower. Do not worry. We come in now. You can give it a name. For example, this is called R2. First configure the address. We configure a left interface. Enter the 00 interface of R2. 192.168.1.2. 24-bit mask. OK. We now open the interface. This is the 00 interface. After that, you need to enter the lookback interface. The way we get in is interface lookback. Usually enter from 0. Configure an IP address. 1.1.1.1. The mask is 4255. Because I want it to be an exact address. And the loopback interface does not need to manually, no shutdown. It is enabled by default. After that, we need to advance to the 00 interface. I need to turn off the function of the device first. That is, first off ARP proxy. Because normally, other equipment from some manufacturers, this function is not enabled by default in the interface. So we close. The same goes for the device on the left. Go to the interface and configure an IP. 192.168.1.1. OK. We open the interface for it. Now let me tell you what I have configured. Don't worry about the command I wrote just now. First, this interface is configured with an address. This interface is configured with IP. Open a loopback interface on this device. And configure an IP. This is the basic configuration now. Now there is a command. We configure the internet address of the device at any time. You must first test whether the direct connection works. That is, R1 goes to test 192.168.1.2 to see if they can pass. If it is connected, it means that there is no configuration error in the direct connection. The reason why I emphasize that everyone has to test whether the direct connection works, because we will involve a lot of configuration in the future. NA stage is not obvious. That is, a few devices involves basic configuration. When you learn NP and IE in the future, you will find there is a large amount of configuration nesting. If you end up with an interface address misconfigured, then there will be a lot of things that need to be changed. So develop a good habit in the early stage. As long as the address is configured, it is necessary to test the direct connection. Now it is connected to the peer. I want to write a static route locally to point out. We still have to enter the configuration mode. IP route. Assumption 1.1.1.1. Go to a precise address. The mask is also 4255. Now write an outgoing interface. If you want to go to 1.1.1.1 now, you have to come out from the 00 interface. I just write an E00. You can view this configuration in the device. Show IP route. You can see this route here. Go to 1.1.1.1. Now go out from the 00 interface. But it's not the same as other routes. It has no next hop. That is, now this exact host. From this interface. Then we now Still need to check the situation of some other interfaces. I ask you a question. Now if I go to ping an address like this, do you think it works? Okay. Can't communicate. Let's check. Check the 00 interface on R1. Here is a MAC address. This is the MAC for the R1 device. Let's also look at the MAC on the R2. For example, a MAC with interface 00. Here we can see its MAC is in this location. This is the MAC of the R2 interface. This is the MAC of the E00 interface of both devices. We can come here and test. Ping 1.1.1.1. Anyway. Now there is routing. Let's see if it works. Unreasonable. If it works now, it means I go to ping a 1.1. Let's consider data encapsulation. Ping uses ICMP. ICMP is encapsulated on 3 layers. Then there are source IP and destination IP in the 3rd layer. The source IP is R1 itself. The destination IP is 1.1.1.1. We encapsulate the source MAC and destination MAC. This is the 2nd floor. This is 3 floors. If this packet can be sent out, and it can also encapsulate the source MAC and the destination MAC, then there will be 1.1.1.1 locally, corresponding to a MAC. That is, local at least. In addition to the current interface MAC. In addition to the parameters corresponding to the interface IP and MAC. There should be some other parameters. That is, next hop current traffic. It stands to reason that it was sent from here. Now it will have a problem. If you configure the next hop to tell R2 its datanet 192.168.1.2 send, then R2 tells R1 whose MAC to encapsulate. R1 encapsulates the MAC of the next hop. So if R1 wants to find its MAC, just send an ARP request. After it receives it, it will reply to R1. But now, the routing table doesn't tell R1 where to go. So whose MAC should R1 go to? Please pay attention. If there is no next hop, the router will choose to ask the MAC of 1.1.1.1. Because it's not telling it to go to 1.1 now. Next hop to go 1.2. Just tell it to send out from the 00 interface. Then it doesn't know it's going to 1.2 at all. So when it goes to ask the MAC, will not ask 1.2 MAC. The destination IP is marked as 1.2. It knows it's going to 1.2. It goes to request 1.2. If you do not mark this 1.2 for it, it only knows that it is going to 1.1. So now it asks for the address. It only requests the MAC corresponding to 1.1. It will send an ARP to ask who is 1.1. But this 1.1 won't give it a reply. Because of cross-network segment. ARP broadcasts can only reach the left interface of R2 at most. Now this lookback is another interface on R2. No matter which virtual interface it is, it must not be in the same network segment as it. Broadcast messages cannot be forwarded. So it can't get its corresponding MAC. It doesn't work. We can check. Show ARP. Check the current ARP on the device. First let me tell you. Why do we have this here? Because just before I configured, I just pinged. See if it works. So it will have. But it doesn't work if you ping. When you do experiments after class. After finishing, you can directly connect without testing. If you don't test the direct connection, you can't get this 1.2 locally. This will not appear in the appearance. You need to know this. But this does not affect our class. It doesn't work. That is, it does not ARP to the destination network. So the broadcast will only be sent here. Then according to the communication principle of ARP, when an interface of R2 receives an ARP packet, it depends on the target IP in ARP. Is R2 himself. Its destination IP is 1.1.1.1. R2 is 192.168.1.2. They are different. In theory, this packet should be dropped. Well, now it does drop the packet. So R1 has no way now. Get the corresponding MAC. Because R2 is not 1.1. So R2 will not respond to this ARP message to R1. Then R1 has no way to encapsulate the 1.1 MAC. R1 local data cannot be encapsulated at layer 2. Data cannot be forwarded normally. By default it doesn't work. But it has something to do with a command I just entered. I turned off the ARP proxy under the interface. Let's say Cisco's device. The ARP proxy function under the interface is enabled by default. So I'm going to turn them off first. You can see the phenomenon. So how can I make it pass now? Now let's test it again. It doesn't work. We can on the device R2 enable the proxy function of ARP for it. Let's take a look together. Enter the 00 interface. I turned on its ARP proxy function. The command to open this is as simple as IP proxy ARP. Proxy ARP. Open now. After opening, let me show you a rather miraculous phenomenon. I will ping 1.1 again. We can observe. It works now. And now, you can check the current ARP table. Now there is ARP to 1.1. But this is the MAC of 192.168.1.1. AABBCC002000. They just pinged each other. So it got its MAC. Let's see now. 1.1 MACs are the same as 1.2. For now R1. When going to 1.1, it thinks that the MAC of 1.1 is the MAC of this interface now. That is, I have enabled the proxy function of ARP under the interface. When R2 receives an ARP message, if target IP is not yourself, but it turns on the ARP proxy, then this data packet R2 will not be lost directly. It depends on whether the local can go to the destination network segment. If possible, R2 uses the interface that received the packet now. Give R1 a reply. Then I will give you a reply now. Because this is one of its local routes. So it is reachable. It will reply to R1. R1 goes to 1.1. The next hop encapsulates R2's MAC. R2 to help R1 forward. Is there a 1.1 route on R2? Let's take a look. Show IP route. Okay. Has this route. This is a local route on R2. So R2 is reachable. R2 can help R1 forward. What the R2 gets is actually its MAC. You will find what we talked about today. Not quite the same as the previous two PCs. It used to be a router between two PCs. Today is two routers. For this thing, it is not fixed. That is, this is only true on Cisco devices. Cisco device interface. The ARP proxy function is enabled by default. So the same experiment. R1 and R2 configure the interface interconnection address. R2 opens a loopback port here. If R2 directly pings, the ping fails. That is, if I write static route here, refers to the current outgoing interface. Equipment from other manufacturers will not work. But Cisco devices can pass through by default. Check it out now on R1. Look at the routing table. I will now change it to a correct. We usually don't write. So I cancel the one just now. It's here. You can cancel before and O. For example, 1.1.1.1. I'll give it the cancellation just now. Then specify the next hop. 0, 0. We cancel it. After cancellation. Now it doesn't exist in my routing table. Now I'm going to write a new one. Copy the previous. Except this. We directly write the next hop. Inside Cisco. Our command to configure the next hop is destination segment. Mask of the destination network segment. Add the IP of the next hop. Just write 192.168.1.2. Write it down and check it later. I now ask you a question. You see I'm in this routing table. Write a route to 1.1. The next hop is 192.168.1.2. But there seems to be no exit interface at the back. For some other routes, there is an outgoing interface behind them. And there is no outgoing interface behind this. If there is no interface, how to forward this route? This involves a function. Route iteration. When the router queries the routing table, it will have a static route addition table principle. The address of the current next hop must be guaranteed. Can be successfully reached through an outgoing interface. The reason why a static route can be added to the table. First of all, make sure the next address of the static route you wrote can be reached through the local outbound interface. Let's keep looking here. I just wrote a static route. Go to 1.1.1.1 next hop. Then you have to guarantee such an address. It must be reachable in the routing table of this device. Then write this static route. Will appear in the routing table. Let me explain to you how to measure whether the next hop is answerable. Just to see if there is a local route to the destination network segment. If there is a local route to the next hop address, then it means that the next hop is reachable. Now make sure that this route is reachable. To add to the routing table. How to ensure that this routing can reach you? There must be a local route that can reach the network segment of this address. Just because there is a local direct connection is 1.0. Or one can find this 1.2 through this direct connection. Then you write the route to which network segment. The next one is 1.2. To take effect. Otherwise it won't work. For us now. You tell me to go to this device in the future. You want to come here. But if for my local, I have no idea how this device works. Then you tell me. Go through this device to the following device. It's pointless. I mark it. 1, 2, 3. You tell me now. If you want to go to 3, you have to go to 2. Then I need to know how to get to 2 locally. If I don't know how to get to 2 on device 1 now, it doesn't make sense for you to tell me to go 3 and go 2. That is, you want to write this next hop now. Then the local must be able to reach this next hop first. I can't say that I can't reach this place. You tell me to give it the data. I can go to the network segment behind it. It doesn't make sense to me. So this is called the addition table of static routing. Measure whether the next item is reachable. Check if there is a route to the destination network segment. Reachable. Next hop address. Can be found through a route in the routing table. So please pay attention. Since I go to such an address, can be found through a local route. So since this data is going to be sent to such an address, then I would use outbound interface of such a route as the outbound interface of this route. This thing is called routing iteration. I want to go to 1.1 now. I'm going to go to 192.168.1.2 first. Then if you want to go to 192.168.1.2, it is on the 192.168.1.0 network segment. This data should be sent out from the 00 interface. That means, if I want to go to 1.1.1.1 in the future, data should be sent from here. Because the next hop belongs to this network segment. Go to this network segment and send out from the 00 interface. So in the future, go to 1.2 and send it like this. Although it is not written, but it's actually in this position. Look for this outgoing interface locally. The iterative function we call routing. Although there is no outgoing interface. But in fact, when forwarding, there are. That is, the process of looking for the outgoing interface of the static route locally on the device. We call it route iteration. Because we are now. I don't know how the outbound interface of this route should be filled. So we need to query the local routing table for other related routes. In this way, the process of determining the outgoing interface is realized. We call this iteration. That is to say, as long as the final data can just reach such an address. We just said, preceded by O stands for OSPF. But what we are actually talking about today is S. Static. So in this routing table, you see the ones that start with S. It means that this one was written manually by me just now. This C stands for connected. How did this direct route come about? Everyone can see. I just did not configure this. But it is generated in the routing table. I only configured a 1.1. So what's going on with this? As long as the interface of this router configured address plus mask, and I now enabled no shutdown for it, the interface starts working. Then a direct route related to it will be formed. And this interface will be used as the outgoing interface. Look at this picture. Now R1 this device. We give it the 00 interface. Configured an IP is 1.1. Then a 24-bit mask of 1.0 will be generated. Because it is a 24-bit mask. A route associated with it. And the outgoing interface is the local interface. This is called direct routing. Well, I have already told you about the conditions for its generation. First, the physical state of the interface is up. And after allocating the IP address, you have to manually no shutdown on the list. That is, the direct route is formed based on the information of the network segment connected under the current interface. Let's talk about the last one. There is an L here. L is called local routing. That is, what interface is configured on this router. Then the IP of this interface. A 32-bit host route will be generated. You can see it here. This is called host routing. Also known as local routing. Its presentation in the table is L. Actually, it is also a direct way. You will find that what is written behind it is the same. This is my device direct connection. It's just that the network segment is called direct connection. L is called local. But in Cisco, it will have a distinction. This is all related to the IP allocation of this interface. Only represent this one host. The most accurate 32-bit mask. This is the host route. Finally, let's do an experiment. This is a basic configuration. This is 3 devices. Open them. Use static. Then let them communicate with each other. Let's do some basic configuration first. Remember how the PC is configured? We configure it with an IP address. 192.168.1.100. This is PC1. Then we will configure its mask later. That is 3255 and 10. 24-bit mask. Then configure a gateway. I have marked the gateway here. 192.168.1.254. PC2 is the same. 192.168.2.100. Then configure the mask. Then configure the gateway. 192.168.2.254. And PC3. 192.168.3.100. Then the mask. Gateway 192.168.3.254. The device is now configured. After, we need to configure the three routers separately. Open them all. Then, let's configure our three. First, change the device name. Everyone should develop good habits. This is our 1. This is our 2. This is our 3. 3 devices. We configure the interconnection address for the interface. Our 3 is the address of the 2 interfaces. First, enter the interface. The interface does not need to return to the original view. Then you can directly from one interface to another. Everyone should know this. Secondly, let me tell you about the configuration format of the address. I made a simple mark here. There will be a basic configuration in the future. For example, on the left here is our 1. On the right here is our 2. Here is our 3. Then we will connect the directly connected network segment between device 1 and device 2, written as 12.1.1.x. Then point 1 is the device on the left. Point 2 is the device on the right. So this interface is 12.1.1.1. It is 12.1.1.2. For us, this is our 2. This is our 3. So what we write here is 23.1.1.2, 23.1.1.3. This serves as the interconnection address between them. Certainly, some students are more accustomed to writing 12.0.0.x. It's all okay. Choose a way you like. When we configure a lot of direct connections in the future, you can tell which equipment this is by looking at it. Okay. This is a brief introduction for you. Just pay attention later. We make a configuration. Here on our 1. We first enter the 0 bar 0 interface. Configure an address. 12.1.1.1. 24-bit mask. Then enter the 0-1 interface. Configure a gateway. 192.168.1.254. Okay. Our 2 is the same. 0-0 interface is 12.1.1.2. And the mask. Then configure the gateway. This is the last device. This process won't last long. 23.1.1.3. 0-1 interface. We have now allocated addresses. Everyone must pay attention. All we have to do now is test the direct connection. Let's test it directly on 3 devices. Our 1 first pings 192.16.8.1.100. That is, ping PC1. See if it works. If it connects, there will be no problem between the 2 ends. Go to ping 12.1.1.2 again. See if it communicates with R2. Also works. So let's finally test. Is R2 connected to 192.168.2.100? Ping 23.1.1.3. OK. Finally. R3 goes to ping 192.168.3.100. So we now do some basic testing. Ensure that there is no problem with the direct connection between each other. Next, we are about to start configuring static routing. Now let's read the title. What we want to do today is use static routing to make three PCs communicate with each other in pairs. The configuration format of a static route is: go to the destination network segment. Mask of the destination network segment. Add the IP address of the next hop. So now I ask you a question. I now want PC1 to be able to reach PC2. That is, I hope 1.100 and 2.100 will work. So let's analyze the process. PC1 is 1.0. PC2 is 2.0. Access across network segments. I will definitely find a gateway. Let's not talk about ARP requesting MAC. Find a gateway. Data here. The destination IP is 2.100. Query the routing table locally. It should not be in the routing table now. Let's check. Show IP route. Not in the routing table. Then the 1.0 network segment cannot go to the 2.0 network segment. So if I now from PC1 here go to ping 192.168.2.100, it sure doesn't work. So for now, it is destination host unreachable. There is no way to reach this device right now. It doesn't work. Now we are going to write a route. Let it pass. IP route 192.168.2.0 network segment. Assuming the mask is 24 bits. Then the next hop is 12.1.1.2. Check it out now. IP route. If under advanced command. If you want to check, you have to add a do in front. Otherwise return hashtag. That is the privileged mode. That's a little slow. So just do show. We can see here. The next hop to the 2.0 network segment is 192.1.1.2. Now there is a route. So can this data come over? Leaving aside the issue of data return. Okay. Able to. So let's recap. Looking for a gateway across network segments. Check your routing table. 1.100 to 2.100 if there is. The next hop is 12.1.1.2. But did not write out the interface. Route iteration locally. To find out which interface should be exited from. 12.1.1.2 local happens to go to 12.1.1.0 network segment. The outgoing interface is 00. I put this packet sent from the 00 interface. And the next hop points to 12.1.1.2. After it receives, this data goes to 2.100. 2.100 also has. Is the network segment of 2.0 directly connected to it? Because they are directly connected segments. So the data can come. Then you can't ping now. Request timed out. For us now. Packet sent out. But it is not possible to ping. Because the data passed. But when the data comes back, PC2 also received. PC2 also wants to reply the packet to PC1. 2.100 received 1.100. When replying to the data packet, the network segment is crossed. It also looks for its gateway. It also depends on its watch. So is there a route to the 1.0 network segment in it? Because 2.100 is going to reply the data packet to 1:100. Then it has to help forward this packet. But without this route, it only has a direct connection 192.168.2.0. 1.0 is not. I should write 1 now. So say we now need to be on R2. To add an IP to it. IP route 192.168.1.0. The next hop is 12.1.1.1. Now we can take a look at local now. The next hop is 1.1.1.2. That happens to go out from the local 00 interface. Because this is its direct connection. Back on R3. R3 to check if the data can reach 1.100. Seems to be able to. The routing table of R3 has this. Because this is its direct connection. So now you can ping. We have now completed the communication. That is, they already have routes between each other. Look. I am referring to a 2.0 here. Pointing to a 1.0 here. Let's quickly talk about the next few. Intercommunication between two PCs. If now this device is 1.100. If you want to visit 3.100. First of all, this device must have a connection to 3.100. It has to have. Then it must have. It is direct. That is. We want to configure once. Configure twice. This is past data. When the data comes back, data flow goes here. It's going to reply to 100. It also needs to be configured once to go to 1.100. 3 configurations. Just finished writing here. This is direct. So in theory, we should configure 3 times. Okay. Let's configure it according to this. You see the hostname here. Don't look at the name above. First of all, we are on the device R1. I am now writing a trip to 3.0. We let 1 and 3 pass. IP route 192.168.3.0. The mask is also 3255 and a 0. Go to 12.1.1.2. This is the next hop. Similarly, we also need to configure the R2 device. 192.168.3.0. Its traffic goes to R2 here. R2 also needs to check how the data passed. Also 3255 and 10. The traffic is lost to the current device. The next hop is 23.1.1.3. Theoretically, the data is now in the past. PC1 sends data access 3.100. Find gateways across network segments. Gateway just wrote. Go to 3.100. Go to 3.0. Next hop go here. Traffic to this device. It checks how to get to 3.100. Discovery is a local direct connection. Data is coming. Terminal receives data. Discovery purpose MAC is it. The destination MAC is the MAC on the link. It must be it. Notice. Between them, they go to make ARP requests. Anyway, it's packaged. Take a look at the 3 layers. The destination IP is also it. This is indeed the data given to it. It wants to reply. Looking for a gateway across network segments. But it won't work if the flow is placed here. It's definitely not working now. Because 1.100 traffic comes back to this device. It will be lost. Because it doesn't. So let's test. Here on PC1. Ping 3.100. It sure doesn't work. We can write a route to make it pass. We write a route to 192.168.1.0. The next hop points to 23.1.1.2. Now the traffic can't come back. Data here. The next hop is dropped to the 0-1 interface of R4. Data coming. Just to configure the intercommunication between PC1 and PC2. This address has already pointed to the 1.0 network segment. So we now write it. After writing it, I can pass it now. So what is missing is actually such a return route. This is the communication between 1 and 3. At last. Let's take a quick look at the communication between R2 and R3. Now I want to communicate between the two. So on which device do I need to write several routes? Data here. This device has just been configured. Going to the 3.0 network segment. Because just now in order to let one and it communicate, data is ultimately forwarded through it. It has to know. So it has been configured with. This traffic is sent here. It will give R5. R5 direct connection will give it. Then we calculate the data reply packet. Back to the current device. 2.100 send data to it. That is the data sent to it by the 2.0 network segment. It has to reply packets. But it doesn't now. We can configure a return route on this device. So now R2 and R3 communicate. We go directly to this device to ping. Ping 192.168.3.100. It doesn't work. Let's configure. Configure an IP here. For example, IP route 192.168.2.0. Then the mask. The next hop is 23.1.1.2. After we have configured, let's go back to this device. Ping 3.100. They go through. For static routing, you may find it complicated. But it's actually not that hard. Just configure a lot of things. Let's sum it up. In order to allow devices to communicate with each other, you will find R3 acts as a gateway for PC1. If PC1 wants to communicate with PC2 PC3, it must have 2.0 and 3.0 network segments. That for this device. It must have 1.0 and 3.0 network segments. For this device. It must have 1.0 and 2.0 network segments. Therefore, each device must be configured. Other network segments that are not connected to itself. So you will find, for the overall static routing configuration, it's just 3 devices. Under 3 devices, there is only one network segment between each. Everyone feels so exhausted. So what about more routers in the future? Will routers have more network segments in the future? In the future, the following terminals may need to be divided into different network segments. Connected to the router. Use static routing. It is actually troublesome to configure. Okay. We'll stop here. Then we also hope that students can follow us. We are ThinkMo Education. I'm Grolin Annesley from ThinkMo. I hope today's content is helpful to you. See you next class. Bye classmates.